All right, let me say a few things about linear independence in spanning sets. If you go to the OneNote notes for LISS, you will find some instructions. Here's a description of 3 types of problems listed under the competencies in this section. So you can scroll down and see this description. What I would like to do for you is go over a different way of doing one of the problems. This is the entire list of problems in the competencies. But here's one problem I want to look at. So here we have a subset of M22 with 3 vectors, and we want to determine if these 3 vectors span M22. All right, so if you go back to here, it says if you want to prove a set is a spanning set for a vector space, it says write an arbitrary vector as a linear combination, row reduce, and see if there's a solution for an arbitrary vector. If so, then the vectors do span. I'm going to use this method on this problem here. All right. So first of all, it said, let's go back there and see what it said again. It says write an arbitrary vector as a linear combination. Okay. All right. So arbitrary vector would be an arbitrary matrix in M22. Right, so let's see how we're going to do this. An arbitrary matrix would be something like, is it going? Let's see. Give me a second. Okay, let's see. I think that works. So an arbitrary vector would be x, y, z, w. That's an arbitrary vector in M22. Now I'm going to write that as a linear combination of these 3. I'll use alpha, beta, gamma. Sorry if you don't like Greek letters. 1, 2, 2, 1. Plus beta times 2, 1 minus 1, 2 plus gamma times 0, 1, 1, 2. Now, if I can find alpha, beta, gamma for any x, y, z, w, that means that these 3 vectors span all of M22. So so the question is, can I find a solution, alpha, beta, gamma solution for any x, y, z, w? Now, this gives me an equation involving matrices. Matrices have 1, 2, 3, 4 entries. Each entry of this equation is giving me a linear equation. For instance, if I look at the top left corner, here I have x. X is equal to alpha times 1 plus beta times 2 plus gamma times 0. Right? That's giving me from the top left corner. If I want to get from the, say, top right corner, I get y equals 2 alpha plus beta plus gamma. So in fact, I get 4 equations for the 4 components. Now, what are the unknowns involved? Well, alpha, beta, gamma, x, y, z, w. Let me just write the first equation. As I said it before, here, let's go back to blue. So the first equation is going to be alpha times 1 plus beta times 2 plus gamma times 0. And then it's going to be equal to x, but let me write that as minus 1 times x. And then let's say plus 0y plus 0z plus 0w is equal to 0. So I'm writing it as a homogeneous equation. Okay, but this is from the first, so let me draw that. This is from the first component. Okay, let's look at the second component. Second component is going to be, well, look at here, this is going to be y, so here it's going to be, so let's leave the y. Here we have alpha times 2 plus beta times 1 plus gamma times 1. Sorry, I forgot the plus there. Plus gamma times 1. And then here I'm going to have that equal to y, but I'm going to put the y on the other side, so I'm going to put plus 0x. And then here I'll have minus 1 times y. plus 0z plus 0w is equal to 0. So that's the next one. Let's go through and do the other two. It's okay. All right, so let's look at the lower left-hand side. So again, I'm doing the alphas, beta, gammas first, and then I'll put the z afterwards. So here's, I get 2 times alpha, so I get alpha times 2. And then I've got minus beta, or beta times minus 1. Okay, then I've got plus gamma times 1. Okay. And then I've got equal to z, but I can write that as plus 0x plus 0y minus 1z, and then plus 0w is equal to 0. And then there's going to be one more equation. I think I can squeeze it in here. I'm going to the w equation here, so it's going to be alpha times 2, alpha times 1 rather, so that's alpha. Then it's going to be beta times 2 plus beta times 2. And then this is going to be plus gamma times 2. And then here I have plus 0x plus 0y plus 0z. And then here I have minus w is equal to 0. All right, now, you might wonder, why did I put the x, y, z, w on the same side? Well, because these are variables, and so I want to put all my variables on one side so I get one big coefficient matrix. Right? So here I have a linear system involving 7 variables. Looks awful, but you've got SAGE to row reduce. So if I put this whole huge matrix of coefficients into SAGE and row reduce, I end up getting this. All right. So looks like an enormous matrix. But my question was, here's my question up here. My question was, can I find alpha, beta, gamma solution for any x, y, z, and w? Okay. Now, the answer is no. And the reason is, given down here, go down a little bit. If you see this matrix here, only y, z, and w are free. X is not free. So that means that I can only specify y, z, and w arbitrary. X is going to be fixed. I can't specify a solution for all x, y, z, w because x is not free. I can only find solutions for a particular x if I know y, z, and w. So in this case, the answer is no. So there's no solution, so that means so, the 3 vectors, so S does not span. M22. Okay, so I hope that's helpful.